Fischer projections are a very useful convention for showing carbohydrate molecules, which tend to have many asymmetric centers, many chiral centers. So, what is a Fischer projection? Well, you take a chiral center, this carbon here is a chiral center, and you project the image two-dimensionally onto a screen. And that is your Fischer projection. What is important is that when you do so, the up and down are going back and the left and right are coming forward. And so when you see this figure, it looks two-dimensional and simplistic, but the way you understand that there's three-dimensional indications in this figure is you recognize the convention. This figure here is equal to this group going back and this group going back, and on the left and right, the groups are coming forward. So try to picture that as like a bow tie. A bow tie. Left and right are coming forward. So remember, up and down is going back, left and right is coming forward. And the way you do this is such that the carbon chain goes up and down. Carbon number 1 is at the top. And another convention is that you show hydrogen atoms. They don't just make them implicit. In this figure of a Fischer projection, if there's a hydrogen on the end of the bond, you want to show it. So let's consider glyceraldehyde. This is an Eldo triose. Another name for it is 2,3-hydroxypropanol. What I'm showing you here is the pair of enantiomers. There's one chiral center. So what we want to do is put carbon 1 at the top and carbon 3 at the bottom. The one on the left, the S form, remember there's an H there. If you were to view this from below, you would see the hydrogen on the right and the OH on the left. The R form, you would see the OH on the right and the H on the left. So there we have our two Fischer projections, one for S-glyceraldehyde, and one for R-glyceraldehyde. So here we have our two forms of glyceraldehyde, R and S, and we have the Fischer projections. There's another type of configuration that can be indicated by the Fischer projection. And that is, you look at the chiral center at the lowest part in the Fischer projection. Here we'll only have one chiral center, but if you had 2, 3, or 4, you would look at the bottom, the lowest, and you notice whether the OH is to the right or to the left on that carbon. So what are these designations? If it's to the right, we call it a D form. If it's to the left, it's an L form. So these are absolute configurations. It's telling you how the molecule is built three-dimensionally. So for glyceraldehyde, we could say for the D form, D-glyceraldehyde, or use its full name, D2,3-dihydroxypropanol, or we could say R, which is the configuration of that chiral center. For glyceraldehyde, there's only one chiral center. So R and D are the same, and S and L are the same. What about optical rotation? Do you remember optical rotation? What if we had a plus in front of the name of a molecule? That would mean that it's dextrorotatory, or minus would be levorotatory. And sometimes people use lowercase d and L. Now remember, optical rotation, dextro and levorotatory, are not absolute configurations. There's no strong rule to equate optical rotation to absolute configuration. It's recommended that you use plus and minus and not D and L for optical rotation, because lowercase d and L gets confused with uppercase D and L, which is an absolute configuration. So why bother with D and L? It really comes in handy when you have multiple chiral centers. So take the Eldo Hexoses. What does that mean? It's got an aldehyde. It's a monosaccharide with an aldehyde, so it's an aldose. And it's 4 carbons long, so it's a tetrose. We can combine that and call that an Eldo Hexoses. Now, how many chiral centers does this have? It's 1, 2. Now, how many stereoisomers does it have? It actually has 4. The maximum it could have is 4, and there's no internal plane of symmetry to cancel out any and form a meso structure. So let's look at the Fischer projections of these 4 stereoisomers. We have 4 stereoisomers. Which of these are the D forms? This one is a D form. This one's a D form. And how do I know that? Because the OH is to the right. These two are L forms. Now, with carbohydrates, we tend to give these common names for monosaccharides. For the Eldo Hexoses, the 2 names are erythros and threose. We have a D and an L form, and these 2 are enantiomers. Why? Because they are mirror images that are not the same. If the 2 OHs are on the same side in the Fischer projection, these are known as erythros. So we have D and L erythros and D and L threose. What if you changed the H and the OH on carbon 3 of D erythros? Without knowing the names, what could you say? It becomes L form, because carbon 3 is the lowest chiral center in the Fischer projection, and it's actually L threose, a diastereomer. What if we change the H and the OH on both of these? What do we get? We get L erythros, the enantiomer. If you have multiple chiral centers and you change the configuration on every one of them, you get the mirror image. And what about on carbon 2 of D3os? Now we're working with this one. Well, it would still a D form. Why do I say that? Because we did not touch the configuration on the lowest chiral center. And we would get D erythros, a diastereomer. Just quickly, let's look at Aldo Pentoses. These are all aldoses that are 5 carbons long. Carbon 1 is the aldehyde carbon. And we have 3 chiral centers. And that gives us 8 stereoisomers. 2 to the third equals 8. There's a mnemonic for knowing these ribs are extra lean: ribose, arabinose, xylose, and lexose. That's if you're working with these a lot and you really need to know the name. I'm not going to put up one of these and say name it. That would be unfair, but there are mnemonics if you need to know them. So ribose has all 3 OHs on the same side, and you have the D in the L form. What about the Eldo Hexoses? Well, now we have 16 stereoisomers, and you can see there are 8 drawn here. What are the other 8? Those would be just the mirror images. So if you wanted, for instance, L-galactose, you would take D-galactose and change all 4 stereochemical centers, their configurations, and you would have the mirror image. These 8 here are the D forms. You can use Fischer projections for ketoses. D-fructose is a keto-hexose. It has a ketone in it. This is carbon 1 up here at the top. The ketone is carbon 2. And we have 3 chiral centers. You're not restricted to aldoses for Fischer projections. I should mention that in nature, D forms are most common.